In contested environments, drones can fail within seconds due to jamming. In this demonstration, we're going to show you how our Arcsynercom can sense the environment, the jamming, and switch the waveform to avoid the failure. I'm Jack Ewell, one of the lead TSN and ISAC engineers here at Agile Radiocom. Today's demonstration will show you OFDM between two software-defined radios, the introduction of a jamming signal, the signal failing, and then showing again with algorithm avoiding the jamming by switching the waveform and keeping the channel healthy. Now this is going to be done fully in hardware in the loop. Over here we have the Atom Pluto, we have the USRB P210. These are our two main transmitters that are connected to these antennas on this main table here. Then we also have our jammer, which is the ZCU 102 and the FCOM S4. This board was programmed for this demo to be the jammer. Our jamming signal is simply our own OFDM signal with a different header, bin allocation, and bits. There are some hardware limitations. The Atom Pluto's USB 2, MATLAB overhead, and our front end make it so that we have a few milliseconds of switching, and because of that we will be using a super frame boundary to do the switch. This allows us to keep the packet error rate down and not lose the connection. Now when we go to the FPGA fabric, this will be solved. We could get sub-millisecond switching. So now to show you the demonstration. Come over here first. We start up this device here. And as that one's coming up, we can start this one. And then we'll see here, we introduce our jammer. And as we can see here, because of that, we have an SNR value here. Our packet error rate is from 0.4 all the way up to 0.57. We have a bit error rate of 0.52 to about 0.6 and higher. The channel is failing. So now we'll restart the test. And this time we'll introduce our algorithm. So we'll reset everything. See, just start that. Start this. That kicks on. Reset. And now we can start this. Now here you can see the RSSI value clicked on, and now we're loading in. Right now we have a good SNR, up around 15. Packet error rate is about 0.01. Bit error rate is 10 to the negative third, right around 5, 10 to the negative third. System's doing really good. Now we're going to come over, introduce our jamming signal. As you can see, the jamming signal is now present. Before, everything shot up, and now we have stability across it because we were able to switch our waveform to DSSS. This demo showed that using the common hardware here, we took RF sensing and was able to make a weak link a reliable and self-healthy link. This is very important for maintaining command and control. It enables reliable ISR, autonomous communication, and command and control never to fail, which other radios can fail at. Now, when we switch this architecture onto the FPGA fabric, we'll be able to achieve sub-millisecond switching. I'll allow my colleague Raul in the next part of the demonstration to go into that further. Thank you.
Such algorithms require hardware that is powerful and reliable enough to perform in the congested environments that our products will be performing at. Let's consider a real-life scenario here. Consider this a drone that is on an ISR mission for the military, which now has an ISR sensor, which is linked to our device through standard interface, which then transmits the data to the receiver. Now we have, to demonstrate that, a Raspberry Pi that is connected to a camera, which then transmits the data to our device here. Now let's click a picture. Which now transmits that data to the device right here, which will start the RF transmission. Now as you can see, this FPGA is too big to be fit on UAVs or other small autonomous vehicles. We could consider something that's smaller like this, but this is not as powerful enough to process our complex algorithms. And so we are working on customizing such boards to be both powerful enough, but at the same time be compact enough and also weigh a lot less compared to something that's as big as these. We also do provide RF front-end reconfigurability, which then the user could swap out for something that is much more powerful, or in case they want to prioritize efficiency, we could use something smaller like that, or sometimes the best of both worlds. Now if you follow me here, the RF front end is connected to an antenna line, which is then here, connected to this antenna, which is transmitting the data. And we come here to this antenna, which is our receiver, which is then connected to an RPA SDR here, connected behind this PC. And here you can see the image which is transmitted.